In today's lesson we're going to look at the physical and chemical properties of the alkene molecules. And you can see here we've drawn out the simplest alkene molecule, which is actually ethene. We've got 2 carbons, we've got the double bond between those 2 carbons. Now the first thing to understand about the alkenes is that they're going to be immiscible with water, they're not going to dissolve in water, and they're also generally going to have very low boiling points. The boiling points of the alkenes, in fact, is very similar to the boiling point of the corresponding alkanes. And the reason for that is that there's only a very, very weak attraction between alkene molecules and between alkene molecules and water molecules. And the reason for that is that there's no dipole really on this molecule. So there's no charge distribution here which could be used to attract another molecule. So if you can imagine another alkene molecule here, drawn out below, draw ethene again. What kind of attraction are we going to have between these molecules? Well, it's a very weak, what we call van der Waals force that attracts these molecules. So how does that arise? Well, basically around this molecule we've got an electron cloud. Each of these bonds here is a covalent bond in which the electrons are shared pretty much equally between the atoms. Okay, but these electrons are not stationary. So if you can imagine the electrons here, they're on the outside of the atoms here, constantly in motion. We've got this electron cloud around the molecule. And as these electrons naturally move around, if we just froze them at an instant in time, we might find that just at one particular instant there's slightly more electrons residing at one side of the molecule than another. And if we have slightly more molecules on this side than on this side, slightly more electrons on this side of the molecule than there are on this side of the molecule, then what we're going to have here is a partially negative charge on the side of the molecule with the more electrons on, and it's partially positive charge with the one that's got less electrons on. And that's what this Greek letter delta is, partial. It's not a full charge, it's a partial charge, a very small charge, because we've just got slightly more electrons in the cloud here. An instant later, it's like they swap around. So this is only there for an instant in time. It's what we call an instantaneous dipole, is this separation of charge. Now, the extra electrons on this side will repel electrons on this molecule and push them away to the other side. So this side of this molecule becomes partially negative, and this side becomes partially positively charged. And so we get what we call an induced dipole in this neighbouring molecule, and then this instantaneous and induced dipoles form an attraction. But that is a really weak attraction because these dipoles are not going to exist for very long. As these electrons move around naturally around the molecule, around the ethene molecule here, that dipole is going to disappear and this attraction is going to disappear. So it's short-lived, it's very weak attraction, and it's very easily broken. And that's why we can easily separate these molecules and we can easily turn a liquid into a gas. So the boiling point is really, really low. Similarly, if we look at a water molecule here, water molecules are strongly polar. So water has a permanent dipole. Okay, quite a significant permanent dipole. And the reason here is that the oxygen atom, located to the right of the periodic table, has got lots of protons in its nucleus, which pulls the electrons. So unlike this bond, where the electrons are sort of in the middle of the bond, the bonding electrons, here they're pulled over towards the oxygen. So those covalently bonded electrons in that covalent bond between the oxygen and hydrogen are naturally pulled over towards the oxygen atom, and the same in this one as well. The electrons are pulled over, so we've got a permanent dipole that exists all the time here with more electrons on the oxygen than the hydrogen, or these bonding electrons residing closer to the oxygen than the hydrogen. We've got this permanent dipole. And for that reason, water molecules interact very, very strongly with each other. And draw another dipole, another water molecule. Now, if ethene is going to dissolve in water, it would have to get in between the attraction between these water molecules. But this is such a strong attraction, this permanent dipole attraction, that these ethene molecules are not going to be able to break into that. And so ethene won't mix with water. It just won't be able to disturb these much stronger bonds that are existing between the water molecules. And therefore, ethene, a couple of properties here. A, it's going to have a low boiling point, but also it's not going to mix with water at all, really. It's going to be immiscible with water. Two key properties of ethene and alkenes in general, really. So we know a little bit about the properties of alkenes. We know that they're going to have low boiling points. We know that they're not going to mix with water. What about chemical properties? Do we know anything about those? Well, let's take an example again of an alkene molecule. Again, let's just take a simple alkene, the simplest alkene, really, ethene. And it will react readily with halogens. So it'll react with bromine water, for example, which contains the molecule bromine, and it'll do that at normal room temperatures. No special conditions needed. And the way molecules react with alkenes is through a reaction mechanism called electrophilic addition. And we're going to talk about what that is. Electrophilic addition. Now, alkanes, where you've just got single bonds, are very unreactive molecules, but alkenes are far more reactive. And it's the presence of this double bond here between the carbons that gives these alkenes this much greater reactivity, because it enables them to participate in these electrophilic addition reactions. The reason for that is we've got a lot of electron density here, these double bonds, and we've got lots of electrons in this region of a molecule. And what that means is that they're going to be susceptible to attack from electrophiles. Now, an electrophile is an electron-rich species, it's an electron-deficient species that will attack an electron-rich center. So electrophiles are looking to attack electron-rich centers, which is what this double bond here actually is. So what happens? Well, if we look at the case of bromine, as the bromine molecule approaches the electron density in this double bond, electrons get repelled. So the electron cloud in the bromine is repelled. It's repelled away from this side of the molecule. The more electrons end up residing on this side, and so we induce a dipole actually in the bromine molecule. So although there's no dipole here at all, the electrons are normally, the bonding electrons are basically in the middle of that bond. But as we approach this double bond here, the electrons, the negatively charged electrons that are present in that double bond, will repel the negatively charged electrons in this bromine molecule, pushing them away onto the far side of the molecule. And so because we end up with more electrons on this side, that becomes partially negative. That's what this delta means, partially negatively charged. And we're left with a small partial positive charge on this side of the molecule. Now what happens then is a pair of electrons in this double bond starts to form an attraction, it starts to form a bond to this bromine molecule here. Now, this curly arrow represents movement of a pair of electrons, so always need to make sure we get this arrow the right way. The electrons are moving from the double bond onto the bromine, so the arrow must come this way down onto the bromine. It mustn't go the other way. The electrons are in the double bond and moving on to the bromine. At the same time, bromine can only form one bond, so as you start to form a new bond between the electrons in the carbon-carbon double bond on this bromine atom, this pair of electrons gets completely transferred across to this bromine here. So what do we produce? Well, the first thing we get is what we call a carbocation intermediate. So basically, this bromine is going to join onto one or other of these carbon atoms. Put it on that one. Because this carbon has lost the electrons in this double bond, it's left now with a full positive charge. And this bromine now has gained the electrons that were in this bromine-bromine bond. So because it's gained those electrons, that gets a negative charge. And that's called a carbocation. Now let's write that down. Carbocation. We've got a carbocation intermediate. And what happens then? We'll just add a double dot here to represent a pair of electrons on the bromide ion. That pair of electrons then is attracted to this positive centre on the carbocation and forms a bond into that carbon. And so what do we get? Well, we're going to get this molecule here, which would be 1,2-dibromo ethane. And there we go. So what we've got here is an electrophilic addition reaction mechanism, which demonstrates how a bromine molecule here adds on to an ethene molecule, forming 1,2-dibromoethane. We could write that out as a chemical equation. So we're starting with C2H4. We're adding a bromine molecule. In terms of a chemical equation, we've got that. And as I say, no special reaction conditions there. That will actually occur between ethene and bromine water. It'll occur at room temperature quite happily. And in fact, that is actually the test for an alkene molecule, because bromine is a sort of an orange, bromine water is sort of an orange liquid, and it's decolorized. Okay, that orange color will disappear, it'll go colorless as the bromine adds across the double bond. So that's the test really, to see if you've got an alkene molecule present. Now, that reaction between alkenes will occur with any halogen molecule. So we could, for example, have the same thing occurring with propene. If we re-added chlorine, for example, and again what we would get is a dichloro molecule, which would be 1,2-dichloropropane. So again, you can see the chlorine molecule here is simply going to add across the double bond. Okay, well, what other reactions could we have with the alkenes? Well, the next thing we can add is a hydrogen halide. So we could add, for example, HCl, hydrogen chloride. Now again, this molecule actually has a permanent dipole. So unlike the halogen, where we induced a dipole as it approached the electrons in the double bond, which repelled the electrons in the molecule, this molecule already has a dipole. What you'll tend to find is any element at the right of the periodic table, and particularly the top right of the periodic table, because it has a large number of protons. The number of protons in the nucleus increases as you go across to the right of the periodic table. Those protons exert a stronger attraction. Positive protons attract the electrons in the bond more and pull them into this side of the molecule. So instead of the electrons residing sort of in the middle of this bond, they're pulled across further to the chlorine, giving that a partial negative charge. So whereas the carbon-hydrogen bond is pretty much non-polar here, this has got a significant dipole. So again, what will happen is the electrons in this bond here will form an attraction, and we can draw a curly arrow here to show the movement of a pair of electrons across from the double bond to the partial positive hydrogen, and at the same time our hydrogen-chlorine bond breaks and the electrons in that bond get transferred fully across to the chlorine. Now what we've got here actually is two possibilities for our carbocation, because this hydrogen could actually add on to this carbon, or it could add on to that carbon. So let's do it both ways. So if the hydrogen adds on to the end carbon, what we will have is a carbocation that looks like this. And the other possibility is we get a let's draw a bit further on, we get a carbocation with the positive charge on the end of the molecule if the hydrogen atom adds on to the second carbon. And also, of course, we're going to get the chlorine here, negative chloride ion. Now what would happen then in the final stage, a pair of electrons on the chlorine will get attracted into this positive centre, and we will add a chlorine on here. So for example on this one, I'll product would be 1-chloropropane. But here it will be 2-chloropropane because we'd add the chlorine onto the second carbon. Now what you tend to find is actually that the major product is this molecule. So you're more likely to find, you'll get both products formed, but you'll get more of this one with the 2-chloropropane. And the reason for that is that this carbocation here is more stable than this one. So it exists, it's around for longer. So the chlorine is more likely to be able to add on to the carbon at this point here. The reason for that is these alkyl groups here, these CH3 groups, are electron donating. So they push electrons into that positive centre and help to spread that positive charge out around the molecule, which makes it more stable. Where here the positive charge is more localised onto this carbon, because it's only got one alkyl group on this side. So this, what we would call the secondary carbocation, with the positive charge on the second carbon, is more stable than it is if that positive charge is on the carbon at the end of the molecule. So because this is more stable, it forms more of the product, but both products are possible. This reaction will work with any hydrogen halides, so HCl we've got here, HBr, hydrogen iodide, they'd all work as well. We can write an equation for the reaction, so we've got 3 carbons, C3, H6 reacting with HCl, and that's giving us C3, H7, Cl. Again, it's an addition reaction. Now another molecule that will react with alkenes is hydrogen. So again, we can add hydrogen across the double bond, but unlike the previous two reactions that we've looked at, this does not occur at room temperature. And in fact, you'll need a catalyst, which will be nickel catalyst, and you'll need a high temperature, roughly 150 degrees Celsius, in order to make the hydrogen molecule add across this double bond. And of course, if the hydrogen does add across the double bond, all you're going to get is an alkane molecule. So we would just form propane here, and we can add the hydrogens on. So we've seen already that we can react halogens with alkenes. We've seen that we can react hydrogen halides, and we can also see now that we can react hydrogen as well. And there's one more molecule that we want to have a look at. The final reaction then involves hydrolyzing the alkene. Now, when we hydrolyze a molecule, what we're doing basically is breaking a bond by reacting it with water. So, H2O. Now, to make this reaction occur, it's not going to happen at room temperature, and in fact we need a catalyst as well. So you would need a concentrated phosphoric acid catalyst, and you would also need a high temperature, about 330 degrees Celsius, and you also need a high pressure. So under the presence of a phosphoric acid catalyst, high temperature and pressure, so at that temperature this is going to be steam. It's going to actually occur in the gaseous phase, this vapor phase. So both the ethene and the H2O are going to be gases. We're reacting at a high temperature and pressure under the presence of an acid catalyst. And in that case, what we're going to do, we're going to be able to add the H2O molecule across this double bond, and we're going to form an alcohol. So for this simple alkene, ethene, we would form ethanol. So it is possible to hydrolyze an alkene in order to form an alcohol, basically by adding H2O across the double bond, but we do need an acid catalyst and we need a high temperature and pressure to make that happen. One other reaction of alkenes that perhaps we should mention before we move on, very important industrially, is polymerization. So alkene molecules can, under certain conditions, react with themselves and form polymers. So for example, ethene, this molecule, we can take a large number, say N, and there's a large number of these alkene molecules. And what we can do is we can actually break the double bond in order to allow one alkene molecule to add on to another. So the ethene molecules can add on, and what you can do, basically, having broken the double bond, you can form extra bonds at each end of the ethene molecule to more molecules. So basically this molecule can be polymerized. This would be what we'll call a monomer, a repeating group, and this would actually add on, and you could have any number of these. So if we had N, a large number of ethene molecules all adding together, we would form this chain with N sets of this monomer all linked together along down the chain. And that's called a polymer. This particular polymer here we formed is polyethene, obviously used in all kinds of things, plastic bags and so forth, polythene.